So we'll continue with this lemma that says that we have a function b that goes from complex number to complex number that verifies that being 0 is 0 and the absolute value of bu minus bb is less than or equal than a constant multiplied by 1 plus the absolute value of u alpha minus 1, b alpha minus 1, u minus b with alpha greater than 1. Then if q is greater than alpha, then the application that goes from u to bu satisfies that the norm in L1, L2 is less than a constant that depends on t and u xt multiplied by t1 minus alpha q, the norm u of xt, and we have a similar estimate for bu minus bb, where xt is in the continuous functions in 0t, L2Rn, intersection LQ, L2 alpha. Okay, so let's make a sketch of the problem. So as b in 0 is equal to 0, we are just going to prove this one. Okay, it will be a specific case of this one. Okay, so then if we have that bu minus bb absolute value is less than or equal than a constant 1 plus u alpha minus 1 plus b alpha minus 1, okay, u minus b, we apply to this the norm in L2, okay, then we will have that this is less than or equal than, okay, so the norm of c1 plus u alpha minus 1 plus b alpha minus 1 u minus b all L2, and this will be equal to, let's say, c u minus b plus u alpha minus 1 u minus b plus b alpha minus 1 u minus b all norm L2. So one can bound this by c, take the c out, and then we get well, for this term it would be u minus minus b L2 plus, now this term is going to be absolute value of u alpha minus 1 u minus b L2 plus this one b alpha minus 1 u minus b L2. Okay, so if we use Hölder inequality, we will obtain that bu minus bb in L2 is less than or equal than c again, and now we will obtain u minus b, this one will stay the same, plus well, now we will have u alpha minus 1, and now we will obtain here L2 alpha plus again, but now with b alpha minus 1 L2 alpha, and now we will have here u minus b norm L2 alpha. Okay, so now if we integrate in the interval 0 t, and again using Hölder inequality, we will now obtain a bound for the norm L1 0 t and in the space L2. The bound will be less than equal. Then let's make some space. So C d u minus b L infinity 0 t L2 plus t1 minus alpha over q u and alpha minus 1 LQ 0 t L2 alpha. Okay, this is going to be multiplied by u minus b in LQ 0 t L2 alpha, and now the remaining term that has to be equally but for b. So b alpha minus 1 LQ 0 t L2 alpha, and now we're having here u minus b LQ 0 t L2 alpha. Okay, and recall that xt is the set where here's LQ 0 t L2 alpha Rn. What do we have here? Okay, and the other side we have L infinity L2. It represents this part. Okay, so for u naught in L2 of Rn, this is 2. Then using this proposition, we get that Wt u naught normal q of b is less than equal than a constant u0 u naught for 2. Using the proposition, we've got that w u naught is in xt, and that the norm of w u naught in xt is less than equal than a constant multiplied by u naught norm L2. Okay, then we can consider the following metric space. Okay, xt u naught equal to u in xt such that u0 is equal to u naught and the norm u minus w u naught xt is less than equal to 1/2. Okay, so let's see that the application gamma defined by, well, gamma u t is equal to wt u naught minus I 0t small t, wt minus s b u s ds. Okay, it's a contraction of xt naught. Okay, contraction. So recall this proposition where we had that G in L Q L P less than equal than CF in L infinity L gamma LR, where PQ and R PQ is an admissible pair and R gamma is a dual admissible pair. And we will consider we will use that 2-1 is an admissible dual pair. So with that we will obtain that the norm of gamma u minus w u naught, the norm L infinity 0t comma L2 is less than equal than CBU L1 0t L2. So using the lemma we just proved, we've got that well, this and again L infinity 0t L2 is less than equal, and now we use the lemma C, constant C that depends on t u x t t1 minus alpha over q norm u xt. Okay, and we can say that this is less than equal than C that depends of t and u xt t1 minus alpha over q, and now we can use the bound for u in xt. That will be 1.5 plus u naught in L2. Okay, so as we have that 1 minus alpha q is positive for t small, we've got that this is less than equal than 1.5. Okay, then this 1.5 here. Okay, so similar arguments prove that gamma is a contraction. So finally, theorem, let alpha between 1 and 1 plus 4 over n, we call this, verifies the integral equation. Okay, then for u naught in L2 exists a unique u in CR L2Rn intersection LQ lock RLPRn for every PQ admissible pair solution of the integral equation we just seen. Okay, and also given T epsilon positive exists delta positive such that if we get a u naught line in L2Rn and the two initial conditions are less than delta, then the maximum of the t's in both solutions have to be less than epsilon.